This is lesson 19 of the Quantum Mechanics, a mini lecture series, Waves Part 1. Now, before moving on to the next atomic model, so after Bohr's model, I need to first make sure that the basics of waves is covered. Okay, so light has been shown to be sometimes a wave and sometimes a particle, okay, depending on which experiment you do. So Dutch physicist Christian Huygens. Now he put forth the wave model of light. He believed that light was a wave, and he explained how light reflects off surfaces. Okay, how it bends when it enters a substance, also known as refraction. Refraction is the bending of light as it passes through a substance. How it diffracts, so how it bends around an obstacle, and how it interferes with itself. So the term wave, best way I can define it, it's basically a moving disturbance which carries energy from place to place. Okay, the most common, or the most easy to visualize wave is that of a water wave. Okay, at the beach, carries energy. Okay, that's why surfers can surf, because the waves carry energy. They move up and down in a very it's not often in chaotic ways, sometimes in regular movements in periodic ways, as it's also called in physics. You can make waves are easy to make. Suppose you take a string and you fix it at some point. Okay, so you attach it to like a hook on a wall, and you move the string up and down. What would you see? You would see a pulse traveling through the string, traveling at some speed v. Now, suppose you've got two pulses generated at each end of a string. So suppose you've got someone holding onto a string here, and you've got someone else holding to a string here. Let's suppose that both of you in sync move the string up and down in a very predictable way. Now, this in practice is almost impossible, because you can't really both make things precise as they are. Let's suppose you've got two peaks moving in opposite directions. If these two peaks, also known as crests, if they meet, okay, one peak meets with another peak, and combined, they give a bigger wave, okay, with a larger amplitude. Amplitude is the height of the wave. If, however, you've got a peak and a trough, so something like this, a peak, a trough is like a dip, okay. Think of a dip, a trough as like the mirror image of a peak, of a wave. They'll combine to give you nothing, a flat line. Okay, they cancel out. The peak and the dip, they cancel out. This first scenario here, that's called constructive interference. Constructive because two waves come together, they combine, and they construct a bigger wave. This scenario here, it's called destructive interference. Destructive interference. Okay, because the two waves come and they basically destroy each other, in other words, right? You can think of it that way. And this is called, in general terms, these two scenarios, it's called the superposition. Okay, when you superimpose, when you add two waves, you get two different scenarios, right? Superposition, okay? And another way to define superposition, if two pulses on a string, okay, travel past a certain point in time, the total distance of the string from its resting position is the sum of the individual displacements. What does that mean? Let's draw a sketch here. Suppose you've got a string that's moving like this, and I was to plot displacement against, let's say, time. Now, displacement in physics is basically a measure of how far you are from your starting point, from the origin, okay? Or you can think of it as a resting point. Okay, displacement can be positive or negative. Positive displacement means you're moving in one direction, negative displacement in another direction. Okay, so positive displacement is this way, negative displacement is this way. Okay, so the distance from a string's resting position, the origin, to its max height, okay, here or even here, where the trough is, the dip is, that's called the displacement.